So let's start about the statistical physics of machine learning today. As you all know, because otherwise you would probably not come to this lecture, deep learning kind of happened in a way that few of us expected, and you don't even need to think these days anymore how to introduce things. If you want to know what's the key progress made in AI in the last 5 years, you just ask the AI. It gives you a pretty accurate answer. So, but I am a physicist, theoretical physicist by nature, and I want to understand the world. And whether this is universe or deep learning, I still want to understand it. So if we understood better what's actually going on in these systems, we would be able to make the models more efficient and hence use less compute, less data for the same performance. We would make it so it's aware of its uncertainty, that it does not hallucinate, that it's actually aware whether it's telling something that it's confident about or not. And it would have the right model of the world from which things that are today discussed often, such as robustness, fairness, explainability, reasoning, at least in the way I see it, would just follow. And my premise is that if we understand better, we can make it better. Okay. So now, before kind of developing on these questions, let me just give you in 3 slides the crash course to a very basic case of what machine learning is, or what deep learning is, so that we can then talk in more concrete terms. So this would be an example of classifying images of cats and dogs. So the computer is given training data. Okay, sorry, this is not working as a pointer, but I was told I have an old-fashioned pointer. The computer is working with the data. These axes would be just ensemble of pictures, and each picture is represented by this long number of 0 ones, because in computers everything is 0 ones. And then each of the pictures has a label which says cat or a dog. And the goal for the computer is to find a function, simply mathematical function, from the x's to the y's, so that if this sequence of 0 ones is fed to the functions, then it outputs 1 for a cat and -1 for a dog. And this should be true for new pictures that were not in the training set. Okay, so that's the goal. Now, how is such a mathematical function found? Well, neural network is nothing but a specific form of this function. So even simpler than that, linear regression, when you have points and you want to fit a line through those points so that the points don't lie far away from the line. That's what we call linear regression. And you can think of it as a particular form of this function where you feed the input x, and it's just a scalar product between a vector of parameters and the data. A neural network is just a simple generalization of that idea where you feed matrices of weights multiplied by the data, then you apply a function that acts on each element of this matrix. And then you apply the same thing again. Now this will be a matrix, you multiply by another one, apply a nonlinearity, etc. several times. And graphically we represent this form of a function by a picture like that, where each of these connections corresponds to a number that is an element of these W matrices that need to be set in a way so that this all works. So in order to understand this, you really just need to know what's multiplication of 2 matrices, and that's enough. Okay, if you don't know that, then think of it as a picture, and we will not need it so much later on. And how is then the training done? Is very simple. You write some natural difference loss function between the labels that you would want on the training set and the current output of what the function is giving you for given values of W. And then you are minimizing over those W. If you imagine this as a function, as a landscape, then you just go down in that landscape in the direction of the steepest gradient. In order to do that on the state-of-the-art systems, you need a lot of data and a lot of GPUs usually. But it's nothing more than that. It's very too simple to explain what deep learning is, and from this we could go and code it. But we don't understand very basic questions about its functioning, about its working, about what is actually being learned. So a question such as, This is an example of some of the data sets that people are often using to explain things about deep learning, which has categories of images. So there are dogs, frogs, etc. There are 10 different categories, 5,000 pictures per category. This is the training set. And then state-of-the-art neural networks have given performance, how good they are at classifying new images of that kind. But if you ask how many samples, how many of these images are truly needed to get a given performance, and if the current systems that we have are close to the minimum or how far away from this minimum or from this optimality they are, we don't know. Nobody is going to give you today a decent, acceptable answer to this question. So to me, if we understood this question, what is the optimal way in terms of the number of samples to actually train these systems, we would be able to then understand them and make them better in the way that I was anticipating. So that's why I will focus on this question. In particular, two forms of this question. So what is the best information theoretically achievable test error? So by test error, I really mean my ability to do this classification. And information theoretically, I mean without the need of actually having an efficient algorithm that will run on a computer. So is it even possible? If I had infinite time, is it even possible? And then, of course, if I cannot do it in reasonable time, then this is not very interesting. So the more interesting question, is this achievable efficiently? That means by an algorithm that will run for some time, I'm okay to wait. And this is not, these questions can be importantly different. Now, the way I approach these two questions, I aim to work in a setting where I can actually answer them very precisely, very crisply. Yet I do not lose what I would consider key ingredients of the system and the interplay between the ingredients. So how do we model the world? How do we model the deep learning? And the key ingredients that I do not want to lose are three of them. They are summarized here in the picture. They are the algorithm that I'm using to search for these weights W to find their settings so that the function gives me the right outputs. There are the architecture, that is how many of these layers, how wide, all these parameters of what are particularities of the architecture take. And they are the structure in the data on which I'm actually trying to learn something. So in my case, these pictures of cars and dogs, etc. But in other application domain, what is really the structure in the data? So why I'm insisting on each of these three ingredients and on their interplay? For the following reason. If I put aside the algorithm, then I have theoretical results about which functions are actually possible to write in the form of the neural network. But those results come without our understanding whether it is actually, something might exist, but it might be hard to find it. So I need to keep the algorithm in the modeling, because otherwise I might be describing something that exists but is impossible for us to find it. So that would not be interesting. I need to be thinking about the structure of the data for the following reason, because it is also theoretically known that for the worst possible structures in the data, this problem of training a neural network is computationally impossible. It's one of these NP-hard problems. It will not be possible to do it efficiently. So I need to be saying, so whatever I'm saying that something is possible, it must be depending on some particular structure in the data that makes it possible. Because I know that for the worst structure, it is impossible. So I have to keep that in consideration. And finally, the architecture, that's kind of the deep learning and the whole point of how these architectures are selected, that interplays with the structure and the algorithm, with the structure of the data and the algorithm. So these are my key ingredients that I don't want to lose track in when I will be creating my models. So now where is the physics? The physics didn't come in yet. Understanding deep learning is also a job for physicists. That was a little piece that I was going around and giving seminars showing this kind of a picture with the structured data architecture and algorithms. And I wrote a little piece about this after giving several of those talks a few years back. And the way we do it, we stand on the shoulders of giants, because in physics, notably in statistical physics of disordered systems, such as magnets that have impurities or glasses in the windows, neural networks have been studied since 40 years. And these would be some of the very influential papers back then in 82, 89, 90 by early works by physicists in this field. And this was coincidentally about the time when the archive.org was established. And because of that, the section that actually is about disordered systems and their physics is called Disordered Systems and Neural Networks. And even today, I took this snapshot, I think yesterday or the day before, you see that there are some disordered systems, some physics, spectra of glasses, Anderson localization, and then you have an exactly solvable model of emergence and scaling laws in the kind of machine learning sense. So even today, it's serving this purpose. So back then, this was really closely linked together. Books were written about this domain, statistical physics of learning, of theory of neural computation, of information processing. So a line of work in those days. And also the Nobel Committee, when they gave the Nobel Prize to Giorgio Parisi 3 years ago, they described his contributions to the physics of random complex materials and phenomena as not only appearing in physics, but also in other very different areas such as mathematics, biology, neuroscience, and machine learning. But of course, we did not need the Nobel Committee in 21 to tell us that we should kind of come back together with the deep learning that came in the last decade and realize that statistical physics that was very present in machine learning 40 years ago and machine learning should come back together. And this is one of the events that we organized in 2018, for instance, where I don't know if you can read the names, but the large part of the community on this interface gathered for 2 weeks in this beautiful place. And those who can read the names, you recognize some of them. Jan Lecan is Stefan Mala, closely related to the Institute, Giulio Biroli, Marc Mézard, Andrea Montanari, Riccardo Zecchina, many others. The more interesting names, of course, are the students at those events, because those will be the important names in the future, but they don't appear on the speaker list. But that's for another story. So we are standing on the shoulders of that work and going after answering those two questions. And the way we will be doing it, as in physics, we need to simplify, to put some of the complications aside, to start to be able to do something. So first, for the first question, what is the best information theoretically achievable error? What is the setting in which we can at least formalize properly the question? And that's actually a setting that already appeared in those papers, in those older paper in physics, that is called the teacher-student setting. So what we do, we will actually not be taking an arbitrary functions between pictures and their labels, but we will specify that we are interested to answer this question in a specific setting where the function itself is given by a neural network. So we will be considering data inputs X, that at this point are generic, and we will consider a given neural network that we choose for given values of weights, those will be the teacher weights, generating the labels. That's the ground truth, the ground truth looks like that by our choice. And then the student network, that we are really the one we are interested to study, observes samples of the inputs and the outputs. The architecture of the network that can only make things simpler, not harder, if we are given that, but crucially does not observe the value of these weights. The values of these weights, it is obtaining in the usual way, the usual kind of machine learning pipelines. It's trying to find values of weights so that from the examples of the samples, it is actually able to learn the right function, the same function as the teacher is using. Okay, so that's the teacher-student setting. And under a setting like that, I can actually formally write what it means to answer this question of information theoretically. Optimal performance in the language of probability. Because the way I define this teacher-student setting, what I actually did, I told you what is the conditional probability of how the labels were created given the inputs and the weights. I also told you some prior distribution of how I actually generated the teacher weights. And if I use that and a simple base formula, I can write the posterior distribution of what were the weights given what I observed, the samples of y and x. And if I'm able to control and compute things about this posterior probability distribution, then the optimal way to predict a new label for a new sample is the following one. I need to take the same function as the neural network is producing, but for which value of weights? Not arbitrary one. I need to average over weights taken from this probability distribution corresponding to the posterior. And that's the optimal answer. That's the answer that in this teacher-student setting, no other procedure can give me a more accurate answer than this procedure. Now, this is actually different from what is usually done in machine learning. The usual pipeline in machine learning is that we write a loss function, minimize it over the weights. For some traditional choices of this loss function, we can regularize or not. So averaging over the posterior is not the usual algorithm used in machine learning. So indeed, in general, we are using, even in this teacher-student setting, we are using something that in general is not optimal. So, okay, that's what it is. Now, we do have the second question. Is this actually efficiently doable? And here, I actually need to do more simplifications because this average over the weights that are taken from the posterior probability distribution, unfortunately, in general, takes exponential time in the size of the system. So we don't know in general how to do this efficiently. So if we want to understand the second question of when it can be done efficiently, we have to simplify further. And going back to what has been done in the line of work coming from statistical physics some decades ago, there are 3 other assumptions under which then I will be able to write a crisp mathematical answer. So now these assumptions are that the data the inputs that I'm feeding into the network are actually IID Gaussian vectors. They have no structure, they're just noise. And the way I'm generating the weights for the teacher network is also IID. Each number is just taken from some distribution PW. And the architecture of the network that has been taken in those early works did not have any of those hidden units. So there was only the input and the output, no hidden units. And general activation function that is used by the teacher. Interestingly, now what will be done to answer the questions? We will actually write the answer in this limit that is called high dimension limit, where the dimensionality of the input is large, the number of samples that the neural network sees is large, but in a way that their ratio is a constant. So this is the thermodynamic limit that in physics allows us to put aside the fact that the physics is probabilistic in nature and compute the density of the air in the room that is a given deterministic constant. And here, even though I define things also probabilistically, everything is random, the weights, the inputs, etc. In this limit, I will be able to write a deterministic quantity that with high probability will be the one that is achieved. For the same reason for which this is done in physics, if I want to describe the properties of the gas in the room, for instance. So here is a slide with the answer. The answer comes, the details, I will show you a few slides with the details afterwards, but they are not so important. It's the form of the answer that I kind of want you to understand. So under the assumptions that I already stated, the answer to our 2 questions, what is the best error achievable, comes in this form. So in the limit, this high dimensional limit, we will have a formula, a function of one variable, m, this will be some real number, m, and studying the properties of the function will imply both the answers on our 2 questions. So this minimum mean square error, that's the one information theoretically achievable with exponentially costly procedures, and one particular algorithm and the error achieved by that algorithm. And the way these are obtained are by examining this formula. If we take its global maximum and subtract it from some number that is given by how the teacher was generating the weights, then we get the optimal performance. And if we take the local maximum that has the lowest m, then we get the performance of this particular algorithm. Now the next 4 slides, if you don't feel very mathematical, you can take a break. But for those who want to see how that function actually looks like, because, okay, I tell you it's a function, okay? Now, this is how the function looks like. Okay, so what this function actually is, where it comes from, is the limit, in the limit I'm considering, of the expectation over the randomness that I put into this model, of the logarithm of the normalization of the posterior that I wrote a few slides back. And the theorem is that in this limit, this function converges to this deterministic value that is given as a function, as a maximum over this m. And the function has this form. So m and m hat are just parameters over which I'm maximizing or minimizing. And this phi pw or phi pout, those are the terms that depend. This one depends on what distribution pw the teacher was using to generate the weights. And this one depends on the activation function that the teacher was using in the neural networks to generate the labels. So those appear here. And then otherwise, this is just some integral over either a Gaussian scalar number or over a scalar number that has the distribution of the weights of the teacher. It's a formula. And from this, what we call free entropy in physics, we can readily write what is the optimal test error just by taking the maximizer and plugging it to yet another formula. That the particular form, you cannot understand like this. One has to work with it, but that's just to give you the form. I was mentioning this algorithm that is described within the same description, the same kind of meta theorem. Here is a pseudocode of the algorithm. It's an iterative algorithm that is using, again, some special functions that are depending on the activation and on the distribution of the teacher weights. And it's iteratively updating variances and means of the pre-activations and variances and means of the weights in a form written here, and it's run from random initialization till convergence, and once it converged, then we compute the estimator from it. The interesting thing about this algorithm is that we can analyze exactly what it actually does at any given time step. That's something called state evolution. It was established mathematically first by Bolhausen in a bit different system for this type of teacher-student setting, later by Montanari. And the way it describes the correlation of the teacher weights and what the algorithm is currently obtaining in a way that is linked back to exactly the same formula that appeared before. So this optimal performance and the performance of this particular algorithm, they are closely linked. They are given by the same formula. It's just if there are several maxima with respect to m, this one may be a different one. That's all. So what does this theory imply? So now, okay, if you ignore the math, maybe come back, because if you still understand the setting and are interested, you will understand. So here is the most kind of canonical example that in physics people are taking to take a special case of this teacher-student setting where the data are Gaussian. The activation is a sign. So these days, the activation function is usually some ReLU, etc. But the sign back then was motivated biologically, so people were often looking at the sign. And the weights are chosen also as a Gaussian. The thermodynamic limit, this high-dimensional limit, is taken. And here I plot the optimal performance as a function of this ratio between the number of samples and the dimension. Red is the optimal prediction. Black is the performance of the algorithm, that in this case is optimal. And blue is some out-of-the-box algorithm, logistic regression, that in this case is close. And we are very close to optimality. So this is an easy case. The out-of-the-box method is very close to the optimum. it's not always nice as that. And the example that I like very much, because it includes a lot of the ingredients that then will appear in the more complicated systems, is the example where the teacher still takes Gaussian weights, but now the activation is an absolute value, and all the numbers are real valued. Now, if the numbers were actually complex valued, then they could represent propagation of light through things. And when we actually do imaging with light, then light can be represented as a complex number, and when we measure its intensity and not the phase. So we lose the phase. So in complex numbers, the analog of the absolute value would be the amplitude losing the phase, and this is a problem called phase retrieval that indeed becomes relevant in a lot of signal processing with light, where we measure the intensity and not the phase. So this is a baby phase retrieval where we only lose the sign because we are working with real numbers. But that's already making things very interesting. So from our point of view, it's just a case of the teacher-student setting as we defined it. And hence the formula applies to it. And hence I can also draw the optimal error as a function of the number of samples over the dimension. And here the curve has a non-trivial behavior. There are actually 2 points at which its behavior changes sharply. The error is as bad as randomly guessing up to half, and then it departs. So there is a phase transition here, and there is another one here where at alpha equal 1, the optimal performance jumps from something so-so to some perfect recovery of the teacher function. And if you look at the algorithm, which is the blue line, it also jumps discontinuedly to perfect recovery of the teacher function, but a bit later. About 13% more samples is needed for the algorithm to work. And this phase in between that seems small here, it's interesting. What's happening here from the mathematical standpoint is exactly the same thing that we actually observe if we want to describe why water changes from, say, liquid water to solid water. The phase transition in water is of a first order type. And if we want to describe this mathematically, we will obtain very, very similarly looking equations as the one that was our formula and that we needed to solve to understand this performance. So this, in all, our understanding is indeed a true phase transition. And the nature of this hard phase, that's the metastable phase of the liquid. So you may know that you may supercool water to, say, -5 degrees Celsius and keep it liquid, which normally it should be ice, but you can actually keep it stable, keep it liquid. Then, say, you pour it here and it crystallizes immediately. That's because it was metastable, and on the way it will also heat up. As it crystallizes, it has lower energy, so it will release the excess energy. So this physics of phase transitions kind of reappears in the phase diagram for this phase retrieval, but in the way that here the algorithm is stacked for exponential time, actually, in the metastable phase and will never escape it in polynomial time. So this phase is predicted hard in some fundamental sense. And there is a line of work about that in computer science. But now for our purpose, I want to kind of keep that in mind. But now I'll go back to my diagram here with my ingredients that I want to keep in mind. So far, we were describing a type of algorithm that is some approximate message passing, that has nice theoretical properties, but is not the one that is used in practice. In practice, we use gradient descent. So can we somehow get more realistic on the algorithm and now say something about the behavior of the gradient descent in this same problem? Still the phase retrieval, the teacher-student setting, not changing that setting. I'm now just changing the algorithm with which I'm actually trying to retrieve the function. And the way this is done, so now this is much closer to the usual pipeline in machine learning. I write a loss. Here, it's still the phase retrieval, so the labels were obtained using the absolute value of the product between the inputs and the weights. And I told to the student network all that information. The only thing I didn't tell is the value of this W star. So a natural loss to write to compare these labels to the products is the square loss, but where I'm subtracting the squares. I know there was the absolute value, so I put everything square, and this way I kind of don't have this problem with having to take care of the two possible signs. This is a very natural loss function for the phase retrieval problem, and we can run it, we can optimize it using the usual gradient descent from a random initialization, going down in the landscape if the axis were the W. And when we do that, and we did that numerically, here on this axis I kind of summarize where we are. So we have already observed that information theoretically I need only more samples than the dimensional to solve this phase retrieval problem to perfection. The approximate message passing algorithm needs 13 more percent. This we read off the phase diagram based on the theory. If we run the gradient descent numerically, we see numerically that we need at least alpha 7. If we go to computer science about proofs about the gradient descent, they are actually quite loose. There are some large constant or polylog d, so they are not very tight. But definitely what we see is that there is a large gap between what the optimal algorithm gives us here and the performance of the gradient descent that is part of the usual pipeline in machine learning. So this is, okay, where is it coming from? Just note for those that heard about machine learning, the kernel regime, the lazy regime, a kernel method would actually need alpha that is scaling with d, not a constant, with d. So d more samples. So that's far away somewhere in other side of Manhattan. So here we are very much in a regime where we are learning features in a non-trivial way. We are really recovering the vector that the teacher used in a non-trivial way, much kind of better than the kernel methods would. But still, we have this gap, and we would like to understand where it comes from and how to get rid of it. And the existence of such a gap, we actually predict that it is closely linked to the existence of this hard phase. Even though the hard phase was so small, just 13%, its presence and its consequences, its physics, glassiness, actually causes the landscape to complicate and causes the gradient descent or other algorithms that are directly walking in the space of weights, such as Langevin sampling or variants of gradient descent, such as stochastic gradient descent, cause all these types of algorithms to have hurdles beyond the hard phase. And that's what we are seeing numerically. Up to 7, the gradient descent is not really doing anything good. Okay, so what to do with it? We remember, or discuss with colleagues in machine learning that tell us, okay, but look, deep learning today is over-parameterized in the sense that it's using a lot of parameters. That's thinking back about our diagram. Indeed, the architectures are such that they actually don't correspond to the ground truth, even when we know the ground truth. They actually use much more parameters. This is a very puzzling property. And the way this kind of manifests is that the usual overfitting, when we do data analysis, we usually talk about overfitting. We should not be using a model that is too complex because it will fit the noise and it will not generalize properly. So that kind of bias variance trade-off that we describe in textbooks, in neural networks, when we take yet many more parameters than even the number of data points we observe, goes away. And we are not overfitting. Instead, with very, very many parameters, the test error is still good. So that's an observation that has been theoretically explained in the linear model, so with the kernel regime. But we are here in a different regime where things are intrinsically non-convex and something that is not linear is happening. But so let's investigate what happens in our problem of phase retrieval when we actually over-parameterize. So we now change the architecture. Now, the way this is done is very simple. Before we had this loss function that was just the square minus the square, and corresponding to the picture with only the inputs in green and outputs in blue. Now we put there one hidden layer that is at least as wide as the dimension. That's what we will need for the next theorem. The way it pops up in the loss function is that now these w's, there is not only one vector of w's, but m of them. And we are summing over them this way, or averaging over them this way. So we are averaging the square. We didn't change anything in how the data are produced. And I'm still telling you how the data are produced. I'm just not telling you the value of W star. So both from a Bayesian and from a modeling the world physics point of view, doing something like that is completely unjustified. We are modeling the system with m times d degrees of freedom, while we know that there are actually only d of them. We know the form. And now we are fitting the function with actually many more. Yet we know it's not true. So this doesn't make much sense in physics. We usually try to model using all the information we have about the system, put it in the model, use it in the model properly. This is not doing that. Yet, okay, let's do it. Run the gradient flow usually initialized. This is a case where we can actually analyze it for particular reasons that are related to the fact that this is a square here and that unfortunately do not generalize as much as we would, the analysis does not generalize as much as we would currently want. But here in a paper that we wrote a couple back with my PhD student and Eric van der Nijden, who's just a bit more downtown here in Manhattan, we showed that in terms of the alpha, the number of samples over dimension that is needed for this over-parametrized way of solving the problem to work perfectly, to recover perfectly the problem, we need alpha 2 and not more. So if I bring it back to my axis here, we needed 7 for the non-over-parametrized case numerically. But now we have a theorem that if in this over-parametrized case, running the same algorithm, the gradient descent, we need 2 and not more. So we largely, not completely close the gap, but largely reduce the gap. So the over-parametrized neural network trained by gradient descent needs fewer samples to solve the phase retrieval. And here I have some comments about that are telling you non-trivial interplay is happening here between the architecture and the algorithm. Right? So I will maybe start with the last comment here. If we stick to this approximate message passing algorithm, over-parametrization would not be helping. That one is already optimal, this we can prove in certain sense under certain class of algorithms. So we would not get improvement from over-parametrization here. But because we were running a suboptimal algorithm, which is the gradient descent, here the over-parametrization could help. So our architectural choice of choosing actually more hidden units was driven by the properties of the algorithm, not properties of the structure. The structure of the data somehow also surely played a role, but here they are not structured, they are just random Gaussian IID. The teacher produces the labels. So it's really about the interplay between the algorithm and architecture that is surprising. And we can observe things like if we put ourselves, for instance, 3 times this number of samples is 3 times the dimension, and we start with few hidden units, we do not get a good performance. We take more and more, and we suddenly start to get a good performance. Well, that looks like the kind of emergence of success with scale, in quotes, because here this doesn't have to be very large neural network, but as it is getting larger, the performance appears, which is something that is, this is a model that reproduces this behavior. And another behavior that it reproduces that even though we need these square parameters to actually manage to train the model to get a good performance, once we trained it, we can generate new labels, and then with the previous method, actually we can solve it and distill it back to D parameters. So once we train the large model, we can distill it back to a small model that has the same performance. So that's again something that we see in the practice of deep learning today. So all that are many reasons for which I like this model. And now I go back again to this picture because said maybe a bit in a simplified way, but one could say it this way. In the past, say, 4 or 5 years, I have been kind of going around this picture and trying to make the algorithm a bit more realistic and the structure in the data a bit more realistic and the architecture a bit more realistic, and doing it in such a way that it's still modular everything with respect to each other, that I'm still taking advantage of the case that I was able to solve before and building my way to something that will understand all the questions that one would want to ask about these systems. So just one slide about the algorithm. We were progressing on something called dynamical mean field theory. So I have seen here colleagues from the condensed matter division that are very familiar with kind of the quantum version of this dynamical mean field theory that we took and generalized a couple years back with my former student Francesca, who is sitting here in the second row, to this teacher-student setting that I'm talking about. And then about that same time, there was a really nice progress in mathematics. For a long time, people were saying this is very difficult to show that this theoretical physics method is actually rigorously grounded. But that was absolutely established 3 years back by, again, Andrea Montanari's group. And Cedric Gerbelo, who was a student in our group, and also Francesca, and we generalized this proof to other cases of interest, the stochastic discrete with momentum accelerated. So now this method is well established within the scope of the setting I'm talking about, and we get some recent nice results for those of you who heard about the information and leap exponents that are describing which functions are hard to learn for the single pass setting. In the multipass setting, these actually are not all as hard as they are in the single pass setting, which was largely surprising to a big part of the community studying these kind of hardness questions. The other of the three ingredients is the data that are structured. So data are not IID Gaussian that have structure. That's a trivial statement. I don't kind of have to write it, but still, for a long time in this line of work, the data were modeled as Gaussian IID and the structure was dismissed. So again, about 5 years ago, or some more than that, we realized that and started to make progress in that direction. And realized one thing, that indeed, real data look like this, but this is actually not real data. This is an output of a generative neural network that is a function into which you feed random IID noise, and it just has been trained. These matrices F have been selected based on data in such a way that what this function outputs actually looks like real data. So the question was, can we take care of structures like that, where F is as generic as possible and C is random, within the framework of the theory? And that's where we made a lot of progress. Starting with simple cases where one just multiplies two random matrices and takes a nonlinearity, which is interesting by itself because that particular case of structure of the data is equivalently describing the performance of all the kernel methods. So that is interesting by itself. So I am not describing in detail. This is more of a mathematical type of progress where we first realized that the theory can generalize to data that are Gaussian mixtures or Gaussians with generic covariance. So this is a mathematical result. And then we realized that under specific conditions that need to be specified in the theorems, there is a type of central limit theorem appearing, or Gaussian universality, that implies that exactly the same result appears for structured data as for those that would just have matching covariance, for some simple neural networks, and data that are either somewhat realistic. For instance, this figure is for the MNIST data, and the points are learning curves of simple neural networks on the MNIST data, and the lines are following from the theory. So here we get a perfect fit, even though the theory works with Gaussian data of a generic covariance. So there have been a lot of progress on characterizing the conditions under which even structured data behave as if they were Gaussian once they are looked only through the performance of the neural network. And these are some of the works in that direction. And this line of work also allowed us to look at things like deriving the scaling exponents in learning with kernel methods, and actually also consolidating the scaling exponents or rates, as they were called, from the literature 20 years ago, because many people studied kernel methods back then, and some of the new ones derived more recently in the physics community, but they were not the same. Nobody really understood why they are not the same. And we clarified that actually one of them were effectively in a noisy case and the other one were effectively in the noiseless case. And when you interpolate between the two, you actually have a crossover between scalings, and in this one diagram kind of unified these disparate lines of work. And a lot of the papers that appeared since that are claiming to do some kind of theory of scaling laws are just special case of this phase diagram, because unfortunately we still don't know how to do something like that beyond the regime where these things are essentially equivalent to kernel methods, which is covered in this diagram. And I'm out of my time. I had a last part on the architecture part, but since I'm out of my time, I will skip it. That was about the fully connected layers that we were describing a lot for a while. We also can say something about the dot product attention layers and see phase transitions there, but in the interest of time, I will go to the conclusion where kind of keeping in the back of my mind this diagram and going around it, making the architecture more complicated. That's the part I skipped. Making the layers, for instance, now dot product attention, not fully connected, looking at these current developments that are happening in large language models, the ingredients that appear there, and putting them in the modeling, putting them into consideration, and answering my two questions on the simplified setting, but very precisely. So I'm somehow going around this phase diagram several times. I would say I make a tour every 2 years or so. So maybe I've done 3 of them so far. And okay, I'm up for more. We are thinking of structured data, hierarchical, beyond this Gaussian equivalence. Benefits of depth in this attention architecture, we actually can take care of multiple layers. And hence we can start thinking of the role of the depth and the role of the different heads and other keywords that appear in those architectures. We are making progress in analyzing the multipath gradient descent, starting to understand what everything does not work for quantifying uncertainty, and hopefully soon things that actually do work. Thinking of generative priors as replacement for sparsity, which very concretely in signal processing is a nice and important topic these days. Thinking about diffusion-based and score-based models and analyzing those as kind of different, say, architectural choices or task choices to make our modeling work. And I'm doing all that, this long-standing research collaboration with Florent Chakala. We have some science research collaboration that also had some byproducts. Happens. If you want to know about some of the methods and details, especially the students in the audience, take a picture of this website where we recorded during COVID our doctoral lecture. So if you want to learn about the replica method, the approximate message passing, and nobody could understand it in the flash that I used. But if you want to send it to your students and make them follow, it's just a semester course, and they learn everything of a lot of the methods that we use. Saying Ingrid here that actually the first version of this lecture happened at Duke when we went there for a semester for a sabbatical. So this is a large part of the people that are working on this with us today, and with this I want to thank you and open for questions.
Thank you for a stimulating lecture. We have time for some questions. Over here.
The first is, how does over-parameterizing actually help? I mean, I would imagine that introduces a number of local minima into your energy surface, which would, that should be bad for gradient descent. And then the second is,
Yeah, so in general, when you introduce more degrees of freedoms, you smoothen things. So this is very intuitive. What is non-intuitive, that by doing that, by smoothing and introducing a lot of new degrees of freedom, you actually did not lose track of where you wanted to get in the first place, the particular points that generalize well. Because by over-parameterizing, you introduce a lot of our spurious global minima, even, that actually do not generalize well. So that's where the result is very interesting, that despite introducing all that new directions and freedom, the gradient descent run in the usual way with no particular hacks actually leads you to a good minimizer. And in the particular case that I was showing, this actually appeared in the fact that not indirectly in the W's, but in the matrix WW transpose, the minimizer is unique in that over-parameterized space for alpha bigger 2. So there we can mathematically understand where it comes from, but intuitively it's not very intuitive.
And the second question, I mean, why, is gradient descent sort of baked in, or could you do some other sort of optimization method that would be kind of non-local, I know, tempered annealing or something that's much better?
So that's exactly the hope, right? That now, because we burn a lot of GPU time because the networks are so large. If we actually figured out how to do it with smaller number of parameters and smaller amount of data, then, and with hence better algorithm, because probably the gradient descent somehow needs the over-parameterization, then we would start answering those big goals at the beginning. So we are not yet there. You would know about that if we would. But we are on the way of getting there. So on the, maybe not on the, say, startup time scale, but on the academic time scale, we definitely are. I believe that. And that's exactly the hope. Come up with better architecture and algorithm, better tuned to the structure in the data, to actually not to have to do it in such a heavy and way that only few very rich companies can do.
Yeah, great talk. So I was wondering, I think there's a feeling in some of the communities at the large companies that when you're training with real world data, that there's a benefit to using synthetic data as well. Like you generate synthetic data, and that helps you train. And I was wondering if are there any precise mathematical results about this improving training?
Okay, so a question, are there any precise mathematical statements in a field where there are thousands of papers every week is difficult to answer. I'm not aware of something that I would find satisfactory. There are pretty solid empirical results of the following nature, that you actually do need the over-parameterization to train a model that generalizes well. But it's a bit similar to one of the comments that I was making about the phase retrieval. But now that you've trained the big one, you can actually produce synthetic labels from the big trained one, and now train a small model on those labels. And now this will work. And you can this way distill your big model into a smaller model while not losing very much on the performance. So you can think of what I showed you as a toy mathematical result, showing that this is indeed possible, right? Showing it in bigger generality, mathematically, as far as I know, is not established, but empirically, the evidence is pretty clear. So that's an interesting kind of, empirical fact we try to explain in broader generality.
Oh, thank you. Thank you for the talk. I'm curious about the thermodynamic limit, and in practice, where we're not working with an asymptotic number of data, is this a very, very good approximation that things do work out deterministically, or are there some meaningful cases where that asymptotic approximation is beginning to fail us?
So where it's beginning to fail us, like surely, right? When we go away from the assumptions of the theory, then it's almost always beginning to fail us. To answer the first part of your question about how large the D and N need to be true to kick in these asymptotics, you actually had some of the plots on the slides. I was not though stating the sizes for which, for instance, these algorithms were run, but typically when D is, say, thousands, and N hence alpha times that, you essentially see no difference between the finite size behavior and the theoretical predictions. So the finite size corrections are small, and we are hitting this thermodynamic limit with pretty decently small systems. This will, you can probably construct examples where, that may be, where it will not be the case, but typically when we derive things and then run on, say, thousands of neurons, we are on the line and it's perfect.
Okay, thank you.
Thank you for a great talk. Just a question about distillation. So when we distill, we preserve performance, but do we lose something? Is there sort of a trade-off, I guess, for example, robustness to the exact values of the weights or something like that? And then also, if you can say something about the uncertainty, I was very curious about that work.
Yeah. So I don't think I have a good answer to your first question about what do we lose when we distill. In the ideal world, I would like to think that we would be able to distill to somehow the true model, and then that kind of helps me to answer the second part of your question. If we had the true model, then the kind of Bayesian way of estimating the uncertainty that is, averaging over the randomness in the true model should be giving us variances that make sense. Now you see why this is not working in the current state of the art, because they are over-parametrized. So they are not corresponding to any true model, right? My example, if you estimate variances in the over-parametrized phase retrieval, those will have nothing to do with actual uncertainty in your phase retrieval. So quite generically, and this is kind of well known, that if you estimate uncertainty in the over-parametrized setting, you actually get overconfidence. And how to cure this overconfidence is, in general, I believe that's why I was kind of putting that as one of the questions. If we were able to answer the question of what is the optimal performance, then it must come with the understanding of what is the actual underlying model. And if we had the actual underlying model, then the Bayesian way of estimating the uncertainty must work. So that's one way of answering it, okay? And the kind of work that we did was going more along the lines, the high-dimensional statistics is bizarre, and none of the guarantees that you have for uncertainty estimation in low-dimensional statistics actually goes through. And standard methods such as subsampling, unsampling, bootstrap, you pick whichever of those you heard about in traditional statistics course, just fail in the high-dimensional regime. This is like one progress towards the uncertainty. Maybe more practical one these days is kind of to train it, to fine-tune it on actually, on reinforce it on caring about the correctness of the answer. That, given the current evolution might be kind of a faster way to progress, that will not allow us to understand again what's going on. So in a longer term, I would kind of like to carry out the first suggested. But I'm happy to chat more about that. To me, it's a very super important topic.
Time for one last question. Antoine.
Hi, it was a very inspiring talk. So
Sorry, it's Antoine. I asked Antoine for that.
Okay, sure.
Well, thanks, Lenka. That was a really great talk. So I didn't quite get how much of the theory or the mathematical results can take into account structured data. So in the teacher-student example, everything was random in the teacher network, yes. Right? The X and the Ws. But people in the field who run numerical experiments say that the structuration of the data is really important.
Yes, it absolutely is. So the progress that I described in a few slides was in a sense in the, say, somewhat like mathematically interesting but somewhat disappointing example, direction, that for the shallow networks where we know how to analyze the training, a lot of the structure, for their performance, a lot of the structure actually doesn't matter. And there is this big universality class where the performance you get actually ignores the higher order correlations and only looks at the Gaussian. So it's some kind of central limit type of theorem. So on that side, there have been a lot of progress, right? And kind of surprisingly realizing how large this class is, up to the point where you run a kernel regression on MNIST and you get the curve, you get the curve. Now, this is, of course, clearly not the end of the story. The structure and the hierarchy must be what drives the depth. And where does this Gaussian universality break? What needs to be true about the architecture and the structure in the data? That's in the current pipelines. So there are, I would say, works on it quite often these days. So hopefully, if you reinvite me, when I made another tour through my diagram, I will tell you more.
Thank you, and we're looking forward to the next tour.
There was a question by Ingrid. I would really, if I may, to go against the chairman and allow this one as well.
This had to do with what you said about the distilling to a much smaller model. That makes me wonder two things. First of all, what happens if you then use that as your initial condition? What does the thing, does it stay close to it or not? And if it does stay close to it, then that suggests that maybe changing the loss function into one in which you add sparsity might get you closer to sparser things to begin with, which are smaller.
In this particular case, it stays close to it. It's indeed a local minima in the landscape that is hidden. Changing the landscape up to a certain extent helps to get there a little bit, not as much as the over-parametrization. Now, putting in some sparsity, okay, I don't know. As far we did not try. That's because the reason for which we can analyze the over-parametrized network is a bit specific to the particular result that we managed to prove about it, and kind of still being able to do it under the setting you're suggesting. Okay, we could do it numerically, surely.
First, take the over-parametrization to have that smoothing, and then when you're close to it, try to sparsify and kind of clinch on I mean, just an idea. That's what I would try.
Yes, that would quite plausibly work. Where it would make me unsatisfied is that I would not be able to analyze it, because it's too. I mean, I could run it numerically, but I would not be able to write a deterministic formula that tells me what exactly is being done. Right, but analyzing the minimizer of the L1 regularized neural network with hidden units, many hidden units, is unfortunately not something that we can so far do. At least if you know how to do that, I'm super happy to discuss. But that's kind of one of the next tour. The problems that we need to crack is to how to actually analyze the gradient descent when the hidden layers are extensive in the dimension on pretty much generic losses. We know how to do it now for particular losses, and not this one.